Hello everyone. Today we're going to talk about another easy topic in linear regression named multicollinearity. Just like last time, I have this folder here that I can save my files in it. Multicollinearity is an issue in linear regression when you have correlation among your right-hand side variables. So when your independent variables are correlated, then you will have this kind of problem. It's okay to have correlation between the dependent variable and the independent variables, and that's the goal of the regression analysis. But when you're doing that, if your right-hand side variables are correlated, you could get misleading results. Two vectors could have a correlation, and one measure that we use to um, evaluate if or whether those two vectors are correlated is the Pearson's correlation coefficient, which you can see the formula of it here. In R, there is a function core that we can use, and easily it will give us the answer. And we will see some of that in an example that we review today. So when you have those correlated right-hand side variables, it's hard to pinpoint the effect of the variables individually on your left-hand side because those variables are could be replaced by each other since they're correlated. An example of that could be if you imagine a group of people that are all singing a song together. It's really hard to, and if you're doing a good job, it's really hard to figure out that who is really contributing to what part of the song. Uh, when you're, for instance, analyzing wage for um, for workers, it's hard if you have age and number of years experience on your right hand side because those two variables are potentially variables that are correlated. As age increases, it's expected that you have higher experience in that job as well. Or like one of the examples that you've seen before, bigger homes tend to have more number of bedrooms. So higher square footage has correlation with higher number of bedrooms, has a positive correlation with that. And if you're using those variables in explaining a left-hand side variable that could be price of the house, you could potentially end up with some problems. Perfect multicollinearity is something that we probably won't see it in practice unless we have some mistake in our data handling. We will review an example of that today too. But perfect multicollinearity is when one variable is exactly the variation in one variable is exactly explained by the other one. So if one variable is a multiple of the other one, that's a perfect multicollinearity. For instance, if x1 is equal 2 times x2, then those two vectors are perfectly correlated. When you use variables like that, you probably, based on different applications that you use, if you want to run a linear regression with right-hand side variables that are perfectly correlated, then you will get an error or something similar. We will see what's going to happen in R when we do something like that. Imperfect correlation or imperfect multicollinearity in this case is when there is a correlation between the variables, but it's not perfect, so it's not exactly equal to +1 or -1, and but still a considerable amount of variation in one variable could be explained by the other one. So if they have positive correlation and you see one variable is going up, you kind of know that the other one should go up too. Or if they have a negative correlation, if one goes up, the other one should go down. Um, so for instance, if the correlation coefficient between x1 and x2 is 0.9, that means that 90% of variation in each of these variables uh, could be explained by the other variable. So when we are running analysis, it's really hard to figure out what variables exactly have what amount of effect on your left hand side. Let's look at these equations. So for instance, if x2 is equal 2 times x1, and we don't want to have a perfect correlation, so we will have some type of error here. So these two are correlated, and then the next step, we want to use them in a model explaining our left-hand side, which is y here. So our model would be y equals alpha plus beta 1 x1 plus beta 2 x2 plus some error term, which is going to be a different error term than what we had above. In this case, the result of the regression analysis would be alpha hat, beta 1 hat, and beta 2 hat. If we substitute what x2 means by the first equation, the second equation, we will get the third one, which is y equal alpha plus beta 1 x1 plus beta 2 multiplied by 2x1 plus a new error term. Now, as we see in the third equation, we have beta 1 x1, and in the second term, we kind of have x1 as well. So when we run the second equation in a linear regression model like LM and R, then what the estimates that we are getting is not exactly telling us the effect of x1 on y or x2 on y, because as we see with that variable substitution, that we are not exactly having those effects separated because of the correlation between x1 and x2 in the first place. Let's open the Multico simulation file in R. R tells me that there's a package using this code that is not installed on this machine, so I'm going to go ahead and install it. You can do the same thing. The name of the package is car. There's a function in that package that we use. That's why we need to install that package first. So what we want to do in this simulation, in the first step, we want to just create 4 vectors, x1, x2, and x3, and x4. They're just normal variables with different means and sometimes different standard deviation too. And Here we have the number of observations 100, and we also have these parameters A, B1, B2, and B3. So what we have is we want to use those parameters in simulating y values. Here's a formula that we're using in our DGP. So we use the parameters that we define above plus the variables that we define above. At the end of it, use this R norm function to generate an error for our equation, and now we're going to have our y variables. Still waiting for the package installation to be over. Done. So let's run the code. We are not using x4 here. We talk about it later. So now using x1, x2, and x3 and the parameters that we define y. Let's look at that correlation function. So I'm using cbind to have y and x1 and x2 and x3 over there in one matrix and insert that matrix into the core function. So let's run that. Remember, having correlation between your y and x's, that's a good thing. But having correlation among your right hand side, that's not something that you're asking for. So we can see that y has high correlation with x3, and then not as much, but still considerable. That's about 0.4. But what we really want to look at is this matrix here, these from second row to the third row to the fourth row and second column to the fourth column, because that's where we can see the correlation between the right hand side variables, and you can see that everything is less than 0.1 except the diagonal elements. So we are good. We don't see any correlation among our right hand side variables. We can run a model. Now we are kind of estimating the parameters that we use in creating this y vector, and this is the results. We use a equal 1, or alpha was 1, here is minus 2.7. It's not that significant, but our beta 1 was 2, and it's very significant, and beta 2 minus 1, beta 3 4, and these estimates are very, very close to what we got. So reasonable outcome. Now let's look at model 2 if we add x4, which was not used in our DGP. So we should expect to not get significant results for x4, and we can see that the t-test results for x4 are not significant at all. And still our estimates for x1, x2, and x3 are very close to what we defined at the top. Now we want to see how in action multicollinearity could cause problem. You remember that in theory we said this could be the reason that we get misleading results. Now let's see what happens in this simulation. What we're gonna do is we're gonna use the same seed number, so everything gonna be the same up to this step. So let's do it together. But here, instead of using the x3 that was used here, what we want to do is we want to use a new x3, which is twice of x 2 multiplied by x2 plus some error, similar to what we have here in x2 and x1. We have a relationship between x3 and x2. And then after that, we want to use x1, x2, and x3, the new x3, and our DGP. So this time in our DGP, there are two right-hand side variables that are correlated, x2 and x3. But x1 and y, that's a positive, kind of shows some, maybe like a little type of positive relationship. Let's look at the correlation. Again, correlation between y and the right-hand side variables is a good thing, but what we really want to see here and we check is correlation between your right-hand side variables, and you can see that x3 and x2, that's like 0.96. That's a very, very, very high number. That is, they're highly correlated. So by that, we kind of know that we're gonna have a multicollinearity problem. So let's run model 1 again, and then look at the summary of it. This time, x2 is not significant at all, and our estimate for x1 is fine, not as fine as it was before, so it's not as accurate as it was. But what is interesting is that our x3 estimate is even way worse, and our x2 estimate is not even significant, as we mentioned earlier. So that is why using correlated variables in the right-hand side, when you create the case of multicollinearity, you will get misleading results. So we cannot really use these estimates and start describing our model and talk about the effect of x's on our y. That's the library that we installed. Now we can call it, and there's this function, various inflation factor function. Various inflation factor function, we're not going to talk about the formula of it, but what it does in practice is it kicks right-hand side variables out one by one and kind of measures how much variation in your whole model was changed because of that. So if you have something that has correlation with other right-hand side variables and then you kick it out, then there would be a lot of variation decreased because of that variables. So if any variable that come up with high VIF results, it's a candidate of having correlation with your right-hand side variables and creating the case of multicollinearity. So perhaps if you kick that variable out, then you will fix your problem. So let's see what we get from VIF here. Typically, VIF values greater than 10 are problematic. You can't really talk about the specific borderlines for problematic VIF versus non-problematic ones. Sometimes you might have the number of observations or other factors could not really show the problem in both ways. You might show a high VIF value, but maybe you have low number of observations. You can't really trust that, or you might have low VIF value, but you know that you have correlation and you're getting results that are not matching the theory. So, but usually when you get VIF values greater than 10, that's problematic. Between 5 and 10, it's something that you need to consider. But less than 5, you're usually fine. but again, usually. So here we can see that VIF factor for um, X2 and X3 are 16. So they're high numbers, and they're showing that we have case of multicollinearity between those two vectors. And we know that that's true because that's exactly how we created that in our DGP. Now, um, previously when we ran X4 in our model, it was the p-value for it was 61, but now that we had the case of multicollinearity, the p-value is lower. So sometimes you may end up with having a variable that should not be significant at all end up to be more significant, and that is another problem with the case of multicollinearity. So one other thing that we talked about was when you calculate the Pearson correlation coefficient, that has a one-to-one correspondence with the simple linear regression R squared. So in simple linear regression, we just have two variables. In this case, x3 and x2 are correlated variables. So if I create a new model n3 and from n3 get R squared and then get the square root of that, that number is exactly equal to the Pearson correlation coefficient. And that you can see here that those two numbers are exactly equal. So this was a simulation to show when we have correlated variables in the right-hand side, you could end up with various problems. That's why we are talking about this topic, and we need to run diagnostics when we are running linear regression to make sure that we don't have case of multicollinearity. That way we can trust our interpretation of the model more. Arthur Goldberger, he came up with the term micronumerosity, which we are making an analogy of it to multicollinearity in this video. Micronumerosity means too few observations. It's the case that when you have not do not have a large data set. So if you have very few observations, let's say 3, 4, or 5, or maybe even 10, um, then you will get very, very inaccurate estimates because you haven't had the chance to see different variation of your data. You're just looking at very, very scarce sample of it. So even with the best tools and techniques out there, you really cannot have anything better than luck in predicting what's going on or describing what's going on. So the problem is not the techniques, is not the tools that you have in your hand, but is lack of data. So no matter how advanced the technique you're using, you you know, as long as you don't have more data, you cannot solve this problem. Sometimes if you have a larger data set, you're showing more and more variation of your uh, variables, and maybe those variables are not that correlated in a larger data set. But when you're using them in a smaller data set, they could end up to be uh, correlated. So one could ask, what is it? cutoff to say that two vectors are having high correlation. So how high is high correlation? Is it 0.9? Is it 0.95? Is it something like 0.97 that we saw over there in the example? And the answer is just like it really depends. You don't have a rule of thumb for it. Generally, if it's greater than 0.7, it's something that uh, it's very high, and it could cause problem in your analysis, in your regression analysis. But sometimes something, you know, higher than that um, could be fine too. But something lower, as low as zero point 0.4, could cause problem. So that's why you need to do multiple things, and we will talk about that. We talked about consequences of multicollinearity. We saw that when we use the case of x2 and x3 when they were correlated, and we saw that we ended up with having misleading results for having less efficient estimates for our significant variables. Uh, your the sign of your variables could change, and those changes could be dramatic. Sometimes you could have a positive effect and uh, statistically significant to some negative effect and statistically significant. Sometimes variables should not have any effect on your left hand side end up to show significance because you're including uh, correlated right hand side variables. Then all your goodness of fit measures going to be misleading too. Your coefficient estimate is going to be misleading. So you cannot really trust the interpretation of your output. However, this is the very, very important thing to remember. Multicollinearity doesn't matter for forecasting or prediction. In forecasting or prediction, what your goal is to minimize the forecasting error. You don't care if the effect of x1 and x2 are exactly separated the way it should, because you don't care about beta 1 and beta 2 separately. You don't care about what's the effect of x1 or y or x2 and y. What you want to do, you want to come up with a model that gives you the best prediction for your y or lowest error value. So in case of multicollinearity, to really figure out what's the effect of x1 and x2, you only can use one of those variables at the same time. But if you want to use them for a prediction case, maybe they even have 0.9 correlation coefficient. There is still 10% variation that is not explained by the other one. So including them in the model could give you more information, better forecasting values. That's why you need to remember that multicollinearity doesn't matter for forecasting and prediction. So if you have a model that has a case of multicollinearity and gives you better forecasting errors, just use that if your goal is prediction. But if your goal is identifying the individual effects of variables on your left-hand side, then multicollinearity is a serious problem. Detecting multicollinearity, we talk about a couple different ways. One was using that correlation coefficient function, the core function in R, to calculate the correlation coefficient of your right-hand side variables and see what's going on. You can visually inspect it to see, have a scatter plot of your right-hand side variables. In this case, for instance, we had x2 and x3 were correlated, so we can plot that, plot x2, plot x3. We can see that there is a positive correlation there. So when you use the scatter plot, just like as it said here, you can see that cigar shape look rather than the round look. Between those two variables, we did that plot x1, x2, we get that cigar shape, but let's do x1, x2 and x3 were correlated. We ended up to have that shape, but let's do plot x1 and x2 that they're not correlated. And we're going to get a more circle shape or like a scatter shape that doesn't show any pattern. We also talk about using VIF and the variation inflation factor to see if it was something greater than 10, it could be problematic. And in our example, there were 16. And we can use that to figure out which variables to remove and mitigate the problem. Let's look at another example. So we have a data set here, house data large. Unlike the previous data set that only had 14 observations for the house sales data, this one has larger number of observations. However, it's not super huge, so it's not like in order of like 100,000s, but it's like a couple thousand observations. So the multi-co-house example is the file that we're going to use and work with that. We're going to clean stuff up from the history of our simulation. Let's clean these plots as well. Clean up our log. So we read the data set, use attach to create the variable names in the background, and there's this GRLIV area, so that has the total square footage of the house, and then beds, this is the number of bedrooms. By adding full bath and then half of, multiply that by the number of half baths by half, summing them up, we get total bath numbers for that house. Here's the CSV file that we read. And you see it has 1,460 observations. And we have sale price. So let's look at density of sale price. As we talk about functional forms section, usually stuff like this, like the price of the house or income or wealth variables, they are variables that they show the difference in the power and the exponent of your variable. So if we take the log of original value, we can get a better, more normal distribution. So now L price is log of price, and we run density of that, and this looks way more normal. So we're going to use that in the left hand side of our model. Our model would be modeling price of the house or log of price of the house using a square footage and number of bathrooms and number of bedrooms. Let's run that, and then let's get the summary of it. So in the summary, we see everything is significant, square footage and positive coefficient. That's that makes sense. As the square footage goes up, the price goes up too. Number of bathrooms goes up, positive coefficient, but number of bedrooms goes up, negative. So that's something that we see. It doesn't make sense. We talked about that before too. Let's look at the correlation between the square footage in bathrooms and bedrooms and baths, or bind them, and then look at the matrix of it. And we see that the smallest number is 0.4, which is the correlation between number of bedrooms and bathrooms. We can also use the VIF function from library car, and here we don't see variables that are values that are greater than 10, not even greater than 5. So this is an example of it, that VIF is not showing us that there is some problem going on here. Let's look at the plot the density between pods. I'm gonna have beds and then baths, because there are specific numbers. I don't really. It's not really jittered here, and there are a lot of points on each other. But you can see that overall, as the number of bedrooms is increasing, number of baths are increasing too. So I have that kind of correlation there. But VIF is not showing me. Now let's look at Model 2. Model 2 is only having square foot and bath, and I get the summary of that. They're both positive, they're both significant, and the VIF of it is still like low values, but that's not the main reason that we're looking at it. And here is the scatter plot of the price versus square footage. We see that it's, as the square footage increases, log of prices increases too. You have these very large properties that were sold like lower than you expect, so that kind of like can skew your analysis. But we just want to run a simple model. Now, this time, because we have multiple right-hand side variables, we just use points instead of line to show our predictions, and use points, call it red for it. You see these levels of different lines on red. Points is just because you have different values of bedrooms and bathrooms, and as you remember, they were in steps. So you don't have 1.7 bathrooms or 2.95 bedrooms. So that's why you see these discrete type of visualization here. And that is our prediction. We can check that with another model that only has square footage, so only one variable, and check the AIC, BIC, and we see that model 2 is better. So it's okay in this case to, use a square footage and bathrooms at the same time in the model, but unlike the other time, that when we had low number of observations in the other case, and we could use the square footage. So what we did, we use combination of VIF and correlation coefficients to figure out if we have case of multicollinearity. Also, the theory helps us too. We know that the number of bedrooms, if it goes up, price of the house should goes up too. So this negative coefficient doesn't make sense, especially when it's significant. In the case of the simulated data, everything was fine. We had high correlation coefficients and we had high VIF values. But in this case, we see that we don't have either of them. We have relatively, high correlation coefficients. They were all greater than 0.4, but they are not much larger than 0.7, unlike what we had in the smaller data set. But VIF values were not large. So we removed bedrooms and only used baths and square footage in our model, and chose model 2 as our best model in this case. So that's what we do in practice. Before coming up with the best model, we reported what was going on when we included the multi-collinear variables in our right-hand side. And then talked about the correlation coefficient, what was the variation inflation factors, and look at the scatter plots of them to see if visually we can detect that correlation too. And after that, we show what's going to happen if we omit those variables and pick the best model from the scenarios that we checked. Another example that we talk about in the bottom of this file, and we finish this section with that, is an example using dataset on car maintenance data. This is coming from Toyota van vehicles, and is a data set of what was the cost of maintenance for these vehicles, and with observations that have recorded age and mileage on those vehicles at the time of maintenance as well. So right off the bat, we know that if a car is older, it's very likely that it has higher mileage on it too, compared to another car that is younger. So if we use age and miles at the same time on the right hand side, we expect to see a case of multicollinearity. Let's go and see what happens. This is our model after reading the data. I think you have the data here too, truck cost.csv, and you have cost, miles, and age in that data set. And here we are showing the summary of our model. And as you see in this case, as miles go up in this model, the estimate is negative and highly significant. It says, so higher mileage ends up to have lower maintenance costs. Again, if we want to have a predictive model, this is not a problem. But if we want to have a descriptive model to be able to individually explain the effect of these right-hand side variables on our left-hand side, we have a case of multicollinearity here, and we have to solve that. So because we see that this is not matching with what's really going on in reality. Here we are showing the scatter plot of miles and age, and you can see that they are very, very correlated. There is almost a perfect line if we connect those dots. And if you run the correlation coefficient of those two vectors, you see that it's almost a perfect, they're almost perfectly correlated. It's 0.996. Well, this is it. That was the end of the multicollinearity section. Thank you.